I'm Ajay Baranwal, Center Director at CDLe, and I'm here to tell you 5 deep learning recipes for mask making industry. Mask inspection, defect categorization, fault detection, hotspot detection, and ability to build, create training data for your applications. These are hard problems which we are trying to solve. And I believe that these challenges, these problems can be solved by deep learning. And in fact, I'm going to show you 5 different ways, 5 recipes which can demonstrate that this can solve the problem. I come from CDLe, which has 3 partners, Mycronic, D2S and NewFlare, and together we have been doing bunch of projects. In fact, in past 1 year, we accomplished 10 such projects which span from supervised learning, unsupervised learning, and reinforcement learning. I'll quickly recap these 3 learning techniques. Supervised learning, which learns from the labeled data, unsupervised learning, which learns from the unlabeled data, and reinforcement learning, which learns to play games. So one example of reinforcement learning in our industry could be iterative optimization, where the software or deep learning agent, it actually iterates itself through the parameters, get the output, and learns from there and improve itself. My 5 recipes, they are based on supervised learning and unsupervised learning. I'll leave the reinforcement learning results for next time. Deep learning is so fast moving technology. Every day, every week, you find that there is a new paper, there is a new deep learning techniques which come in. And the moment it happens, the first thing I think in my mind is that how can I apply those techniques to our mask industry problem. And you will see the same thought process in the recipes. In each recipe, I take real world example which has been benefited from the deep learning, and then I'll try to map it to our problem and show the techniques which were used, and then I'll show you the results. So let me jump into my recipes. The first recipe is categorization of design mask error checks. And the real world example which comes is from recommendation system from Amazon and Netflix. Amazon and Netflix, they use recommendation system, recommendation engine to improve their user acquisition and also to improve their user experience. That happens using similarity of products and similarity of movies. And that idea we took for the mask rule check error categorization. So a typical mask rule check tool, it can create thousands of errors, and some of the errors would be very similar to each other, and there is a need to kind of group those errors together so that the engineer can understand them in easier manner. And here, as you can see, I have 8 such example of errors. So these errors come from, these are spacing error or EP error, and the top left and right and bottom middle 2 images, as you can see, these are spacing error, and they need to be grouped together because they share the same layout. So is the case with the middle top 2 images and bottom left and right 2 images. The bottom left and right 2 images, they have EP error with respect to the CAD data, and as you can see, these 8 error images, they need to be grouped into 3, and we'll see them how. We'll use a similarity amongst them and then use it. In order to capture the similarity, autoencoders are a great technique. Actually, there has been there forever, for a long time, and they are used to reduce the dimensionality of the numerical representation, and also they used to capture the similarity of the input data. For example, in this case, the left image, I have taken a mask image clip, and pushed to the autoencoder, and then I get a vector which has series of numbers, and those numbers are also called embedding or encoding, and using those encoding we have been able to group these errors very nicely. As you can see, out of those 8 images we have 3 different groups. So that was pretty promising. I'll go to my second recipe. My second recipe is the fast mask design construction, and the real world idea comes from medical imaging, diagnostics of human brain tumor using the MRI scan, and it came. This technique came in 2015, I guess. Named the neural network type was used UNIT, and using UNIT, the engineers were able to actually diagnose, pinpoint, segment out the problematic brain portion. As you can see on the right side picture, it has the red circle actually encapsulate the region which has problem. We applied this to accelerate the simulation of short list to mask dose map. And this is required for understanding the downstream impact for evaluation with different configuration of the shortlist, and to be able to see how the mask shape is going to look like. And if you see this problem, I mean, being as a modeling expert, we know that this is a hard problem, but looking at a different approach to this problem, there is an image on the left hand side and there is an image on the right hand side, and we are trying to actually convert the input image, left image to right image. And in order to do that, we use UNIT. UNIT architecture is very powerful to kind of do image to image translation. UNIT has a structure which has U, as the name says, and it downsamples the input image and then upsamples to the output image, and also to capture details of the image at every level there are horizontal connection, and we use this to construct the mask dose map from the short list, and we could see 2.5x improvement in runtime, which was pretty promising, and we are actually working to improve it even further. And let's look at the accuracy of this model. So in order to get the accuracy, we took the constructed dose map, and also we took the original simulated dose map. We took the contour, we took the EP, edge placement error, and then we compared. And the maximum EP error was less than 5 nanometer, and this was, sorry, less than 3 nanometer, and it was pretty promising for us. I'll move to the third recipe. Now the third recipe does not come from photomask industry. This is for error classification. However, the same concept can be applied to defect classification in mask industry. And the real world example was Amazon Go. Amazon Go is a physical store which does not have registers. So pretty much you walk into the store, you pick the stuff, what you want to buy, and just go out. You do not need to go to a checkout counter, and this is possible with bunch of deep learning techniques. The most prominent ones are object detection, object classification, and we actually use the object classification for pick and place machine. So in the PCB assembly line, there are components, there are parts, IC parts, and then they needed to be placed on the PCB, and there is a machine called as pick and place machine. It does exactly what the name says. It picks the components and then it places to the PCB. Now it's very important to pick the component correctly with the correct position and correct angle so that it can be placed correctly, otherwise there will be yield problem for the PCB. And in order to monitor that, there are cameras on the bottom, as you can see in the middle picture, and it keeps taking images, and based on the image classification, the machine decides whether it can the component can be mounted on the PCB or it has to be disregarded. And this is pretty difficult task, because these machines, the pick and place machines, these can be different machines at different customers or in different batches. They have different cameras. The camera can have different noise. It can be taken from different angle. in fact, if you see the middle picture, that has a very bad image which doesn't give any information. So the classical computer vision does not work here because those are based on handcrafted feature engineering, while as deep learning based approach, because it can learn the features through the filters, and this is an example of VGG16net, which actually has convolution. So it has 16 layers, and each layer has convolution, 3 by 3 convolution, and the convolution is able to pick the local information, and then the deeper we go into network, higher the number of filters are, and those are the filters which learns the feature automatically. And using that, we were able to actually achieve 99.76% of accuracy, which was pretty promising and awesome, because even the human accuracy is 90% to 95%, and this was 99.76%. And you can see some examples of the bad picked components like billboarded, tombstone, wrong pick angle, and then also example of OK. Alright, let me move to my fourth and second last recipe. This recipe comes from flat panel display mask making industry, and the real world example comes from fraud detection. Now fraud detection is a very hard problem to learn for deep learning even, and the reason is because some of the frauds, I mean each fraud is of a different type, new type of fraud, and you have not seen that. So you need to have an unsupervised method of learning where you can learn the normal cases so well so that any abnormal case comes in, it should be able to flag it out. And let's see how we applied it. So for flat panel, muras are irregularities or defects in the mask writing, and when the mask is being written on the panel, every XY position there are some parameters which are recorded, which could be deviation to the expected one, and those deviations are color coded to a surface log, and then we use the surface log to find the anomalies or outliers for that. And the deep learning technique which we use it, in this case we have used GAN, Generative Adversarial Network Framework, where the goal is to learn the data distribution of the normal cases, normal plates so well that any irregularities in the plate can be identified. And using that, you can see the results. We were able to get very good results. There are two plates actually. On the right hand side you see there are irregularities, muras, and on the bottom plate there are two places, and on the right hand side is the result of the deep learning output, and all those bright regions, as you can see on the top and bottom, they are actually the muras. This was so powerful and very encouraging to us to apply deep learning technique. Alright, so I would like to go to the last recipe now, and the last recipe is the digital twins creation. And digital twins are complex systems which are built using a lot of data, a lot of sensors, a lot of physics based simulation, and also deep learning. And the deep learning techniques which it uses are some of the mixture models, GANs, and even reinforcement learning. I will show you two examples. The first one is same digital twin, where we could create the same images based on the CAD data, and the second one is the ILT digital twin, where we could construct the mask shapes from the target shape even with the assist features. So that was pretty awesome. So alright, so I kind of I'm done with my 5 recipes. I just want to recap that I showed you 5 different problems, 5 different deep learning ways to kind of solve those problems, and not just that, I showed 5 different neural network types, starting from unit structure, deep autoencoders, deep anomaly detection, deep convolution network, and also the mixture models. And I would like to conclude my talk by asking you a question. Do you see there is an anomaly in this picture? Yes, very well, because there is a red fish and its direction is also different. As a human, we can very well tell that there is an anomaly here. And so is true with the deep learning. Deep learning also has advanced to a state where you can identify this red fish. In fact, deep learning may not know the context, but it will know that there are some entities which has eyes, which has fin, and its direction is different. How about now? Can you still find? Yes, a little bit effort, and even a person who has color blindness, he can also identify that there is a fish which has different direction and it's an outlier. So can deep learning do. In fact, even instead of an image of fish, if it was a picture of house, picture of car, even then we could have done that. How about now? You see where I am going. The more the data becomes, the human starts making mistake, human gets tired, human gets bored. And however, deep learning does not suffer with that. Deep learning keeps on running on modern hardware and it can do the job for you. So pretty much any place where you see that there is an application where your human expert, your engineer can see the data, can see some images, can see something and say that, oh, I see there's some pattern, there's some problem. Deep learning is your friend actually. And that's exactly what I have been able to show to my all 5 recipes. Thank you very much.